Hey everyone, I just want to go over some details and also some intro for those of you who may find this helpful. This is Fulton Virtual Algebra 2 Unit 3 project. This is the fundamental theorem of algebra. So I want to kind of go through this a little bit. Hopefully this will help you as you are trying to make progress with this particular project. So here's the overview. Fundamental theorem of algebra is basically it tells us that the degree of the polynomial, right? Degree of the polynomial, if you were to line them up in standard form, it's going to be the highest degree that we see in that polynomial. So degree of polynomial, it tells us the total number of solutions or roots for that function. Okay, so let's start off with an easy example here. We have y equals x cubed minus 2x. There's no parentheses here. There's nothing to expand, nothing to distribute. So we pinpoint, we identify the highest degree, which is 3. So this is what we call a third degree or degree 3 polynomial. So if this is a third degree polynomial, then there should be 3 solutions. Okay. When we think of solutions, many times we think of x-intercepts. We're going to go into some more detail as to, not all solutions may be x-intercepts, but the straightforward ones, yes, they're going to, a lot of times, the number of x-intercepts we see is going to be a number of solutions. So I want to kind of show you that, let's say I want to plug this in the calculator. Okay, either you have a graphing calculator, or if you don't, you can go to Desmos.com. So let me show you. Let's plug in this x cubed minus 3x. Okay, if I type in x cubed minus 3x, sorry, x cubed minus 2x, this is what the graph looks like. And we can clearly see that we can identify, we can point to 3 x-intercepts. So we have 3 x-intercepts. That matches the degree of our polynomial. So we can identify, okay, these are our 3 solutions or roots. And we call them real roots because we actually can see them cross the x-axis. So this polynomial has 3 real roots or solutions. I want to just kind of go show you real quick how you can see a graph in Desmos. You may need to be able to see a graph in Desmos. So if you go to Desmos.com, okay, and then click on Graphing Calculator. And now we're going to enter in x cubed minus 2x. So you go to this blinking cursor to the left, and you're going to do x. And then to get that exponent, you're going to do shift 6. Shift 6 has a little caret above the 6. And then it's going to, that cursor is going to go into the exponent position. So we go x cubed, move that cursor down, move to the right, minus 2x. And we can clearly see, you can put your mouse or your finger on your screen, and you can move it around. You can definitely tell we have 3 x-intercepts, right? We have 3 real solutions. So that's to kind of show you an easy version of how we can pinpoint roots, but not all the problems will be that straightforward. So I want to kind of start with an easy one, and then we'll look at a more complex one or more involved one. So here's example 2. Example 2 is x minus 4 cubed times x squared plus 1. Now, this is not standard form, meaning that it's not like the previous problem where we don't have any parentheses to expand. Here, we need to expand, but we're going to try to avoid that. And the way we can avoid expanding and be able to decide the degree of this polynomial is we identify the highest number in each parentheses. So this is x, this is cubed, this is squared, and we're going to add those 2 exponents together. So 3 plus 2 is 5. So if we were to expand everything out, this is going to be a 5th degree polynomial. Now, just because it's 5th degree or 5th degree polynomial, it doesn't mean like the previous problem where we're always going to get x-intercepts. So just because we have 3 solutions, for instance, it doesn't mean that a 3rd degree polynomial will always have 3 real roots. So I want to talk about imaginary or complex roots for this particular example. Now, a degree 5 polynomial still does mean that there are 5 solutions, just like how a third degree polynomial will have 3 solutions, 4th degree polynomial will have 4 solutions. But let's expand the definition of a solution. A solution can be either a real root or imaginary, or what we call complex roots. So real roots are ones that we can physically see across the x-axis. Complex roots are ones that we cannot see. And sometimes we may not see all of the solutions. The previous example, we could see all the solutions. But here's the general rule. The general rule is that we have 5 total roots. They could be a combination of different roots between real and complex as long as they add up to be 5. Okay, so we know that these 2 are going to add up to be 5. Now, the previous example, it just so happens that we have 3 real roots, 0 complex roots. So 3 plus 0 equals 3. So this still holds true, but it's not going to be true for every problem. Now, here's another restriction. The other restriction is that complex roots have to be an even number. So 0, 2, 4, 6. We can't just have 1 real root or 3, we can't just have 1 complex root or 3 complex roots. So before we look at this problem, I want to show you the possibilities that could happen if we were to add the 2 roots together. So let's look at the possibilities that we can combine numbers and add up to be 5. So we could have 5 reals and 0 complex, right? This is okay. This is a true possibility because 0 is an even number, and so this is a possibility that could happen. Could we have 4 real and 1 complex? It does add up to be 5, but 1 is not an even number, so this is not a valid possibility. Okay. How about 3 and 2? 2 is an even number. 3 plus 2 equals 5. That's true, so we can keep this option. 2 plus 3 we can't do, even though it adds up to be 5. 3 is an odd number, so it doesn't fit that complex a restriction that we have. 1 and 4 is fine because 4 is an even number. 0 and 5 we have to eliminate because 5 is not an even number. So without even looking at this particular problem, we know that we must have either 5 and 0, 3 real, 2 complex, or 1 real and 4 complex, right? These are the only possible options that can work for our problem. Now let's go to our problem. X minus 4 cubed times x squared plus 1. If I set both equal to 0, I can find this algebraically. So this is really x minus 4 times x minus 4 times x minus 4. If we set all of them equal to 0, we get x equals 4, x equals 4, x equals 4, x equals 4. Now these are 3 real roots, even though they are even though we see repeated solutions, we still consider this as 3 real solutions. Okay. Now over here, x squared plus 1, if we set that equal to 0, we'll get x squared equals -1. Take the square root, we get square root of -1. And this is imaginary number. When we take the square root of both sides, a plus or minus will show up. And square root of -1 plus or minus square root of -1, these are 2 imaginary or 2 complex solutions. So we have 3 real, even though it's repeated, it's still 3 real numbers. We have 2 complex, so 3 plus 2 equals 5. Now, does this fall under a category that we said could happen? Yes, 3 real and 2 complex can happen. And if you were to graph this, okay, you can put this in Desmos, you're going to see that this graph is going to cross through x equals 4 once, but we can see that it's counted as 3 solutions because that x minus 4 cubed, we have repeated instances of x minus 4. So even though we see it only once, it's because it's being repeated 3 times. And then we don't see the other 2 solutions because they are in the, they are considered complex, imaginary. They're not within the real number system, but we still count it as 2. Okay. All right, so hopefully this will help you get started with your project, and good luck. Hopefully you guys find this helpful and you'll be able to make good progress with your project.